Hi, I'm Chem's best friend. If you need chemistry help, the information how to contact me is on the bottom of your screen. So hello, welcome back. In the last video, we learned about light. We talked about light as being part of electromagnetic spectrum. And why did we talk about light? Well, remember, we were stuck at Rutherford's nuclear model of an atom, that atom is mostly empty space. Electrons are flying around empty space, and we want to know where are the electrons? What are they doing? Where are they? Would that help us explain chemical behavior of elements or chemical reactions? So we talked about how there is emission spectra of elements, and each element has unique emission spectra, its own unique fingerprint. So let's go to my screen and start. So here is the emission spectra of hydrogen atom. So what's going on is, maybe you see this in your classroom, there is this long, thin light bulb filled with hydrogen gas. We connect it to electric outlet, we connect it to energy, it lights up, and if you look at it through this prism, you're going to see that it produces these 4 lines, very distinct 4 lines. So red, kind of like greenish turquoise, blue, and a very, very dark violet. Sometimes you cannot even see this line. Okay, so what's going on? Why does each element emit unique emission spectrum? Well, Niels Bohr also wanted to know this. And Niels Bohr had this equation, Rydberg equation. And here is the equation, what it was. So the question is, people could explain, actually put mathematical formula to explain the spacing between these lines and the wavelengths. But the question is why? How did it work? What did this signify? So you have math equation, but what does that mean? And Niels Bohr comes up with planetary model of an atom, and he says, I know what an atom looks like. He says, and to explain this, he says, an atom must look like this. So we have a nucleus, and then we have these orbits, and with each orbit corresponds in a way energy layer. So each orbit has specific energy. And electrons, which I have in little green dots, can only sit on these specific orbits. Electron cannot be here, cannot be anywhere between these orbits, so it's not possible. Now, if you input energy, if an electron absorbs energy, it can jump from a lower energy to a higher energy, from a lower orbit to an orbit farther away from the nucleus. So electron can move to an excited higher orbit. But then electron, you remember opposites attract in chemistry, right? Electron, which is negatively charged, is attracted to the nucleus. So electron will want to fall back to a lower orbit, lower energy level. So it will go down, and when it goes down, it releases energy. So absorb energy, move farther away from the nucleus to a higher energy level or higher orbit, and when electron wants to go back, it goes back, it releases energy. And we have, this orbit 1, 2, 3, and what's interesting is the spacing between these orbits, the spacing between first and second orbit is the biggest jump. Then the spacing between second and third orbit is smaller jump, and then again smaller jump, and keeps going. It gets smaller, 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 smaller. Okay? So he says that. So, and then remember, energy is directly proportional to frequency. In a way, this also looks like this. So if you go from energy from third to second orbit, it's less energy than from fourth to second, which is still less energy, less jump than from 5 to 2 or from 6 to 2. And I drew right here that everything going to energy number 2 actually is the 4 lines of hydrogen spectrum. So remember, hydrogen spectrum had red, turquoise, blue, and violet. And here is actually the 4. And I also drew the specific, like trying to show wavelengths. So red wavelength is the longest, and then violet is the shortest, highest frequency. But if an electron goes to orbit number 1, right, it's a bigger jump. You're going to add this much space, right, this much jump. So all of these will actually be in the UV region. Everything finishing with energy number 2 jumps are in the visible region. These are the 4 lines of hydrogen spectra. Anything going to first energy layer is in the UV region, where anything going to third energy layer is less energy, infrared region. So in this you can actually see what happens if you go to a 4th energy layer and 5th energy layer. So Bohr says everything is on an orbit. Electron can only be on specific orbits. Electrons cannot be in between. So how do they get there? How can they get there? Really interesting. But let's actually do some calculations to see if it works, right? So let's try it. So here we're going to calculate the wavelength of light of an electron growing from 4th energy layer orbit to 2nd orbit. What color is it? So here is the Rydberg equation, here it is, and we're going to just plug in the numbers. So we're going from N4 to N2. So what is here is my N final squared and initial squared. So we're going from, excuse me, so final we end up on 2, we start with 4. So we're going to initial, and we're going to plug in. So we have 1/4 minus 1/16. You plug this all into a calculator, you're going to have energy is negative 4.09 times 10 to the negative 19 joules per that 1 photon. Negative number, what does it tell you? That means energy is released. Yes, so energy is released when electrons are going from higher orbit to lower orbit. And the numbers, the math tells us that. So if we have energy is, here is energy, and again, frequency equals energy divided by Planck's constant. We plug in these numbers, and we get, here is my frequency, 6.17 times 10 to the 14 hertz, or per second. And again, C equals lambda nu. I'm going to have my speed of light divided by frequency. I'm going to get my wavelength. I plug in the numbers and I get 4.86 times 10 to the negative 7 meters. Change it to nanometers, that's 486 nanometers. Wait a minute, 486 nanometers? I look, and here it is. Actually right there. That's right there. 486 nanometers, that's the turquoise. Right, that's that turquoise light. And this is why, right here, going from 4 to 2, you release energy and it will be that turquoise light. That's why I drew that. So is this making sense? So you can plug in any number, any initial, energy 6, 5, 4, 3, finishing at 2, and you will get the wavelengths corresponding to the emission spectra of hydrogen atom. You will get all these numbers. Okay? Now, what happens if we do that bigger jump, going to n equals 1? Let's do that. What about starting at 5th energy level, 5th orbit, going to 1st? So again, bigger jump should be more energy, right? So it should be in the UV region. Let's actually see if the numbers make sense. So here is our Rydberg equation. We have final is, what's my final? 1st energy layer. What's my initial? I'm starting at 5. So here we have 5 squared, 1 squared. You plug in the numbers, just plug this in, and this is your energy. Again, your energy is negative, which is released. Tells us that energy is released. And you plug into our energy is directly proportional to frequency, E equals h nu, and you will get your frequency. And then speed of light, C equals lambda nu, plug this in, you will get the wavelength. and it's 94 nanometers. Well, 94 nanometers, let's think about it. Visible light is between 400 and 750. 400 is violet, yes, 750 is red. So this is what's more than violet, ultraviolet, UV region. And this is exactly what this light says. If you're going to anywhere in N equals 1, you will wind up in UV region. Try it. So Bohr says, I can explain this math. Yes, he says, I can explain this math. And using this equation, and I can actually explain what's going on, why we have this emission spectra, where the electrons are. So Bohr says electrons are on orbits. Now, this is really cool, because this helps us also explain some flame tests for metal ions. Maybe you did a lab like this in your school. Based on the specific color of a flame, you can figure out what metal ion gives off the specific flame color. Now, why? Remember, each element, each atom, each element will have a specific number of protons in the nucleus, and that means it will have its electrons arranged in a specific way. And now they will say electrons repel one another, so they will be a little bit pushed away. They are attracted to more protons. So each element will have a very specific orbit arrangement, a little bit, shifted a tiny bit. And this is why each element will give off specific different colors, which is really, really interesting. Okay, but there was limitations to the Bohr model. Now, here are the limitations. It works only for hydrogen atom. It still works today for hydrogen atom. So don't tell me that Bohr model is all wrong. It still does a great job for hydrogen atom, even today. Well, what's special about hydrogen atom? It has only one electron. So the moment you add more electrons, remember electrons, same charge, repel one another, Bohr model falls apart a little bit. And here it does not explain why an electron does not fall into the nucleus of a hydrogen atom or any atom. So if we said how electrons are attracted to the nucleus and they want to be in an energy level that's closest to the nucleus, what actually prevents them from falling into the nucleus? All the electrons should fall into all the nuclei, but they don't. And Bohr couldn't explain why. He just say, well, they don't, because they don't. It's not a good explanation in science. And also does not touch anything on the periodic table, right? Remember, it's 40 years after Mendeleev developed periodic table. And Bohr model does not help us with that. So today, we covered Bohr model of an atom, and we see that clearly the story has to continue. So the story will continue in the next video. But for now, thanks for watching. See you next time.